Hello everyone, welcome back to my channel. So many friends are interested in representation learning. So today I will be covering some very recent hot topic of representation learning, which is contrastive learning. So why is contrastive learning so powerful and popular? So let's dive into it, have a look. Okay. So remember that the supervised end-to-end training for image classification, it generally adopts some cross-entropy laws. So the goal of it is to predict the labels of the data instances, right? For example, if the image contains a dog, then the classifier should directly tell you by inputting the data instance, the classifier or the model itself directly learns to predict the label of that data instance. So that is the goal of the supervised end-to-end cross-entropy training. So in contrast, contrastive learning instead, because there's no typically no label information in the self-supervised manner. So the model has to learn to find patterns among the data instances themselves, right? So in the case of contrastive learning, what the model is trying to do is that it is trying to predict whether the data instances are similar to each other or not. For example, given a random data pair, like two dog images, right? In principle, the model should be able to tell that the two images contain the same underlying concept, and they should be treated similarly. Okay, so basically that is a goal, right? The model is asked to identify the similarity among the data instances. Okay, so let me introduce a very popular framework or famous framework in the field of contrastive learning, which is SimCLR. Simple framework for contrastive representation learning from Google Research. Okay, so let me turn on the laser pointer here. So the general framework is like this. Okay, so for any given input image X, okay, it is transformed into two augmented views of the original image, which are called xi_d and xj_d. Okay, using some form of transformation T and T prime. So the transformation here is generally something from the random data augmentation perspective. For most of the cases, like for example, there could be like random cropping, random color jittering, etc. Okay, because the two data instances, the two augmented views originate from the same data instance X, that they are considered as similar to each other. Okay. As the next step, the two instances xi_d and xj_d are fed into the encoder network. Okay, the encoder network is something that is typically very powerful, such as deep neural network. Okay, which is able to retrieve useful patterns from the input data. For example, if the input if the input is images, then typically the encoder could be something like ResNet50 or something like that. Okay, and then the according representations Hi and Hj are acquired. Okay, as the output of the encoder. As the next step, there is another extra component, which is the projection head. So the projection head is typically something like a multi-layer perceptron. Okay, so the reason that the authors adopt the projection head is that empirically speaking, it brings better performance. Okay, and there is another perspective that projection head really helps, is that it can help degrade the dimensionality of the encoded representations into something smaller dimensionalities. For example, Hi and Hj can be something like 2048. But if we want to compare the similarity among data instances, we should hopefully get something smaller, right? Because similarity calculation is actually costing a lot of computation also, right? So Zi and Zj could be something much smaller, for example, 128, okay? So Zi and Zj would be the projected embeddings or projected representations, okay? And the contrastive loss is formed upon Zi and Zj and other projected embeddings in the same data batch. And in this case, Zi and Zj are considered similar to each other because they originate from the same original data instance. So the contrastive loss is trying to maximize the agreement between the two or maximize the similarity between the two. So the similarity measure could be something really simple, right? If Zi and Zj are normalized into unit vectors, then we could typically adopt something like dot product to direct compute the similarity, okay? Okay, let's formally look at the loss formulation, okay? The loss is called the N4NCE loss. And this is firstly brought up in the contrastive predictive coding paper. Okay, the motivation is that you want to maximize the similarity. You want to maximize the mutual information between two variables, for example, Zi and Zj. Okay, and by deriving a mathematical bond, this is equivalent to maximize the similarity between the two. Okay, so here, as we can see that for instance I and j that originate from the same original data instance. Okay, so this, remember, Z stands for the projected embeddings or projected representations of the original data instance. Okay, so Zi and Zj are put onto the numerator. Okay, and if they're similar, then this value is going to be large. So here tau is another hyperparameter which stands for temperature. Okay, so if Zi and Zj are similar to each other, then this value is going to be large. Okay, and because there's a negative block here, so the loss is going to be small. Okay, so this loss actually encourages high similarity among similar instances. Okay, and in the denominator, for the instance I, it goes through each remaining instance in the data batch except itself. Okay, so basically sum over all of them. So for the rest of the instances that are not similar to the instance I, the loss also encourages the value of them to the similarity value of them to be small, right? Because if the denominator is smaller and the numerator is larger, then this loss is going to be smaller. Okay, so the meaning of this loss is that in the projected representation space, the similar examples are encouraged to be embedded, similarly to close enough to each other, while dissimilar examples are encouraged to be embedded far apart from each other. Okay. So a very interesting empirical finding from the SimCLR paper is that if you look at the trend of the SimCLR performance on the classification task from ImageNet data set, and as you increase the number of parameters or increase the model capacity to a certain level, it can actually reach a comparable performance or similar level of performance as its supervised counterpart. Okay, so as you can see, these two values are very close to each other. Okay, which means that a larger model really, improves the capability of self-supervised contrastive learning. Okay. So there's another version of SimCLR, which is called version 2, and they extend the work into the semi-supervised setting. Okay, so on the first look, we can see that the process or the pipeline is divided into 3 stages. Okay, so the first stage, okay, So the first stage, there are massive amount of unlabeled data. So the authors utilize them to train a big deep neural network, in this case, a big convolutional neural network, which hopefully give us some good representations that can generalize to different downstream tasks without any prior information, right? So they train the unlabeled data on the task agnostic neural network, and then they attach few layers of projection heads. Again, the projection heads are found to be useful for the model performance, okay? And do this kind of unsupervised pre-training. Okay, this is going to be the first stage. And the second stage, the middle part here, and they fine-tune this pre-trained model using the small fraction of data that has class labels. So the small fraction of labeled data, okay, they do some supervised fine-tuning. And this actually is going to be very helpful, as we can see later on in the empirical results, okay? At the third stage, which is going to be the downstream task stage, okay, there will be some, task-related data, and some tasks to be finished, and they utilize something very interesting called distillation. Okay, so what distillation does in this case is that there is a teacher network, which is the pre-trained big convolutional neural network, and there's a student network, which is a task-specific network that is going to be adopted to make predictions on the ancient data. So what they do is that they ask the student network to mimic the behavior or the prediction of the teacher network. For example, on a certain image that contains a dog, if the teacher network is telling you that, okay, this image should be classified as a dog image, then the student network is trying to match its own prediction with the one from the teacher network, okay? And actually, they find this distillation process is very powerful for the downstream task performance, okay? So 3 stages, again, first stage is the pre-training, unsupervised pre-training stage, okay? So a massive amount of unlabeled data is used in this stage, okay? And also the projection head actually help with the pre-training. The second stage, they use only a small percentage of labeled data to fine-tune, okay? And the third stage is basically utilizing the distillation process to learn a task-specific network or student network to make predictions, okay? Okay. So some very interesting empirical findings from the SimCLR version 2 paper. So as we can see here, in this one, if we just adopt a very small percentage label, like 1%, right? It helps actually, the SimCLR version 2 approach, it helps greatly outperform the state-of-the-art approach, okay? And if they increase the label percentage into something bigger, like 10%, a very encouraging thing is that if you use a larger model or model of larger capacity, as you can see here, it greatly outperforms the supervised counterpart, which means that the small fraction of labeled data actually greatly helps in the case of contrastive learning, right? It's actually a large margin, although it's a bigger model, right? But if you use like the same model capacity, right, it can still outperform the supervised counterpart by like a smaller margin, right? So there are a few conclusions from the 2 papers, the version 1 and the version 2. So first of all, the larger batch size actually greatly helps with the training of the contrastive learning model. Why is the case? Because, if you think about it, the contrastive learning actually compares the data instances themselves and drawing similarity conclusions from them, right? If you have a larger batch size, which means that when you contrast one example with the others, then you have more contrast power, right? You have more information, and the model can get a better understanding of the similarity conclusion or similarity information among the data instances. That can give you a more complete overview of what should be similar and what should not be similar, right? So larger batch size definitely help in the case of contrastive learning. And the drawback is very obvious, right? Because there are computation graphs, right? You have to store those information. So typically speaking, the computation is going to be very large if you want contrastive learning to work very well, right? So the implication of this is that there is a lot of computation needed. And the second point is that it involves like longer training times if you want to improve the performance of contrastive learning. And again, this means that more computation actually helps. Third point, larger models. As we see before, right? If you increase the capacity to a certain level, it can reach a very, very comparable performance as the supervised counterparts, right? And the larger model actually benefits both the self-supervised case and the semi-supervised case. Again, this means that you should have more computation, right? And the next point is that the distillation, as we saw just now, greatly benefits the semi-supervised setting. Okay. The last point, of course, is that larger projection head models actually bring better representations. Again, you should have more computation. So as we see here, the majority of the conclusions from the contrastive learning is about computation. So indeed, that contrastive learning is very impressive in terms of model performance or downstream task performance. But the price, there is no free lunch, right? You have to pay the price. And the price is that you have to pay for more computational resources. Okay. Okay. I'm going to talk about a very, very interesting and amazing work that I'm personally very interested in, which is the OpenAI CLIP model. Okay, which is very exciting. Why do I think this work is exciting? Because this is kind of like a multi-modality work in the contrastive learning setting. Okay, the previous work we have looked at pretty much fall upon the same single modality scenario. Okay, so only images are used. Okay. But in this case, two modalities, okay? So the first one is natural language, and the second one is the images, okay? The two forms of input representations are adopted, okay? So why is this one powerful? So let me talk about the intuition or thoughts at the end, okay? But let me first of all introduce the pipeline or the procedure here, okay? So of course you need two encoders, right? Because you have two forms of data representations. So the first one is natural language, then you need a text encoder, okay? The second one is image, you need an image encoder. And typically speaking, the text encoder could just be some like transformers, right? And the image encoder can either be, vision transformers or the deep convolutional neural network, okay? So how do they acquire the data? So you can imagine there are massive amount of data on the internet, and you can get this paired data between the image and, for example, its according text description, right? You can easily get this kind of data from the internet, okay? So each image is paired with one single sentence that describes the content of the image. For example, this pop image, right? It contains the pop object inside the image, and the text description tells you that actually this image is also about a pop, right? So basically, they share the same underlying concept to some extent, okay? So what they do is that they feed the bunch of images into the image encoder and get their according representations, I1 all the way to IN, okay? Same here, and accordingly, there are N text representations, and they're fed into the text encoder, and the according representations or projective representations are T1 all the way to Tn, okay? So I1 all the way to In, and T1 all the way to Tn, okay? So the thing they're trying to do here is that they try to match each image with its according text description or text representation, okay? So I1 is supposed to be represented similarly with T1 in the embedding space, and I2 is supposed to be represented similarly or close enough to T2 in the representation space, all the way to IN and Tn, because they originate from the same data pair, okay? The rest of the entries, they should not be too similar to each other because they do not, originate from the same image and text pair, okay? So as you can see, the similarity here forms kind of a diagonal here, okay? Okay, so this is a pre-training stage. Remember, there are massive amounts of data, right? They adopted to train the text encoder as well as the image encoder. Now is the time to utilize those pre-trained representers to do some downstream tasks for us. For example, let's just do a simple image classification task. You have a pool of candidate labels, right? Like playing card, dog, all the way to bird, right? What you do at this stage is that you don't need any task-specific or task-related fine-tuning. You don't need that, right? They assume that the pre-trained models are already capable enough, okay? And they can be directly used to do the zero-shot prediction. So first of all, they fed the pool of candidate labels into the text encoder to get their according representations, right? There are already a ton of text representations being trained. So for any input descriptions, they hopefully get some very good representations that represent their input concepts well. So T1 all the way to Tn. Okay, for the input image in question, okay, same thing. For example, here it's a dog image, right? It can be fed into the image encoder to get its according representation, okay? In order to get the prediction of the label class, okay, or the image class, what they can do is that it can directly match the image representation with the according text representation entrance, and then find the similarity, highest similarity score. For example, I1 and T3 gives us the highest similarity score, and that will be the prediction of the model in this downstream task. Okay. For example, here it successfully predicts that this image is about a dog. Okay. Interesting, right? So why is it so powerful? Why is it like multimodality really helpful here? So I have a simple understanding, right? So because the input information there from two different forms of representation, the text as well as the images, okay? So basically, there are also noises in each form of representations, but the different representations, they share the same underlying concept. For example, this is a pop, or this is also about a pop, right? So the network will try to focus, or the model will try to focus more on the shared underlying concept in two forms of representations, rather than focusing too much on the input noises, okay, on each single modality, okay? So for example, this background here could be a distraction for the model prediction, okay? But this kind of a distraction is not the same thing in another modality, okay? There could be some other distraction or other forms of noises in the text descriptions, but they don't typically share the same form of distractions or noises. But the only thing they share is the underlying concept, which is pop, right? The pop object and the pop concept here, right? So in order to match them together in the representation space, the model should try to capture the shared underlying concept instead of something else, right? So I think that is the most amazing place of you know, the multimodality training pipeline. Okay, that is also, you know, a little bit of my thoughts. Okay. Okay, so let's look at some very interesting results here. So, for example, they use the pre-trained model into doing some very interesting classification tasks. For example, here they put a television studio image and they put some very similar, you know, very confusing or very similar concepts here. The conference room, lecture room, they're not too different from each other, right? But the model is still able to, you know, successfully recognize, you know, tell the concept of the image with a very high confidence. Okay, same thing here for the kangaroo object. So this is from their official blog. If you're interested, then you can browse some more exciting examples there. Okay. So we have been, up to this point, we have been looking at, you know, the self-supervised case of contrastive learning, as well as a little bit on the semi-supervised scenario. So someone may ask, what if we, you know, generalize the contrastive power or contrastive learning capability in those case of supervised learning, right? If we add extra information, which is label information, is that going to be more powerful? Okay. And the answer is yes. Okay. So let's look at the two different approaches. Okay. So the self-supervised contrastive learning, let's review it a little bit. So for any anchor image, so the anchor is something that is being contrasted. Okay. So for example, this dog image here, the positive example will be another transformation of the same dog image. For example, this is transformation 1 of the original image. This is transformation 2 of the original image. Okay, and they originate from the same dog image. Okay, and when this one is used as the anchor, and this dog image will be used as a positive example because they originate from the, remember that they originate from the same image, and that's the reason that it should be treated similarly in the embedding space. Okay. And the negative examples are, of course, you know, some images that contain objects from different classes, okay, as well as other dog images. So you notice something, you know, that shouldn't be there, right? Because, for example, this dog image, although it's from a different original image, but they actually share the same underlying concept, but they are treated wrongly as negative examples. So this is no good, right? But we have to do this. We have no choice in the case of self-supervised, you know, contrastive learning. But now if we add the extra layer of information with the label information, then we can know that the dogs, they're from the same class, right? The dog images, although they could originate from different original images, but they are actually from the same class, and they should share the same underlying concept. Thus, they should be treated similarly in the embedding space. Okay, so in the case of supervised contrastive learning, the other images of the original class are also put into into the positive example set. Okay, for example, this anchor image, the positive example would be another transformed dog image. Okay, and as well as the dog images, that originate from different original images, and the negative examples are just the ones from different classes. Okay, in the data batch, in the mini batch. Okay. So is this actually helpful? So let's take a look. It actually greatly helps. Okay. So first of all, let's look at the difference between the two losses. The first of all is import NCE loss, as we have seen just now, right? For any particular mini batch I, okay, it loops through every single instance or augmented instance in the mini batch, okay, small I, capital I, okay, and find the according similar example, positive example, which is denoted as JI, okay, and they should be treated similarly, remember, and in the denominator, okay. It goes through the rest of the examples. So basically AI stands for the entire mini batch except itself, okay? And then sum over them, okay? But here in the supervised contrastive loss, because there are a lot of positive examples, remember that in the self-supervised case, the only positive example is another augmented view of the original image, right? But in the case of supervised contrastive learning, all of the examples in the mini batch with the same labels are positive examples. So in this case, okay, the authors need to loop through all of them. Okay, so they define a positive side for the instance I. Okay, and the positive side basically contains the examples of the same classes in the mini batch, okay? And then each of the data pairs should be treated similarly in the embedding space. And the denominator here, again, works as the normalization term, okay? And again, there's a negative sign here. So it encourages a larger, a larger scale of the numerator and a smaller scale of denominator, okay? So as some very interesting exam results here, they show on their GitHub repo that if they compare the TSN embeddings between the supervised contrastive learning and the SimCLR models, actually they find that if they let the projected representations to be of dimensionality 128, okay, and then they do this kind of TSN visualizations, they find that compared to SimCLR, actually supervised contrastive learning models give more, give closer embeddings within the same class and more distant embeddings among different classes. So, which is very interesting and encouraging, right? Which means that the extra layer of supervision that come from the label themselves are actually very helpful in the case of contrastive learning. So as a summary, okay, there are some takeaway points. The contrastive learning is very powerful, as we have seen just now, especially in the self-supervised scenario where the label information is absent or it is too expensive to ask, human experts to manually label them, okay? And secondly, okay, it largely benefits from several points, such as larger batch sizes, larger, models, which means that for it to work very, very well, you have to have a large amount of computational resources, right? And thirdly, most of the findings in this domain are still empirical. There are not too many papers that really, support the efficiency of contrastive learning. I think one very famous one is from Princeton University. They kind of, gave some theories behind the contrastive learning, but overall speaking, most of the findings in this domain are still like empirical work. Okay. Okay, so that's going to be all of the content I want to cover today. Thanks very much for listening to my presentation, and hopefully you get some, interesting perspectives from today's talk. And hopefully you can get some pointers to, for example, if you're a scientist, you get some pointers on what set of papers to look at. Obviously, there are more papers in this domain that are, very successful, very encouraging, but I do not have time to cover them in a single presentation. But yeah, hopefully you get something very useful. So thanks again, and looking forward to seeing you in the future videos. Okay.